Okay, thank you very much for the opportunity to present at this conference. This is a new forum for me. I'm coming from university, so it's the first time I'm presenting for developers. So I hope that I found the right topic and entrance to the presentation. I will speak about the construction of functional programs, and in that way I will try to emphasize the way you may actually construct a program from some kind of specification, and in this case here my entry to that will be some simple type formulations of types and signatures for functions. This will be my entrance here. So the method I'll present is actually the core of a new book with a very good colleague of mine, Hans Reichhardt, which came out last year, and there is a lot of supporting material for that book, so hopefully you'll have a look at it. If I look at some often claimed advantages of functional programming, then people may say they are typically much shorter. The efficiency is not worse than what you see in C#. Since you're writing less code, you may actually develop faster. So you may actually, since you're writing less code, make fewer bugs. And in combining all this, actually more complex problems may be within reach of being solvable. Now, there is a special style you use when you use functional programs. You are not having states or mutable states, and that means it's much more easy to exploit multi-cores, parallelize your programs. So some of the headlines of this is that you may say that functional programs are usually succinct, they are as efficient as mainstream programming languages, there are benefits sometimes to market on correctness, and one can say abstraction also. You express yourself in an abstract way, and what does it mean? I would say it means that you're expressing yourself closer to the concepts of the applications. So there are meanwhile a lot of success stories of functional programs. In this fsharp.org website, there are a lot of testimonials from people using F# in various contexts, telling what is good about it. This is a more general website by Phil Wadler for functional programming languages in general, or not just F# that I'll be basing this talk about. What are advantages? Then Simon Cousins have a website where he actually, for some projects that were performed in some mainstream languages and F#, there are some comparisons. So this all sounds very good, but please notice that failures are not very frequently reported. So these are success stories. There may be other stories. And in general, when you compare things, it's usually on a not so solid basis. So all these things you should, of course, understand with care. So this table is one taken from a paper by Simon Cousins. It's based on an application from the UK energy industry, where a project first being performed using C# failed or not succeeded in all aspects, and then a later project completed using F# actually fulfilled all the requirements of the applications. And I'll not go into what it did, what the project was about, but just mention some figures here. You can see the number of total lines in the code is about 10 times shorter for the F# project. You can see there are actually more brackets in the C# project than there are code lines in F#. What is perhaps more important is the null checks in the C# code. There are very many, 3,000, huge amount. And in the F# code, it's very short. So, of course, this is, I think, basically an unfair comparison, because the guys doing the F# project actually learned from the failures of the first one. But there is some indication that functional programs may be succinct, they may be more easy to get correct, and there are not so much null checks. So what does that mean? That's actually the functional style of programming. It's because when you construct a functional program, it's basically value-oriented. So you are not working with data structures, you are working with things like list and trees as they are values. It means that you have, in a way, no pointers. You have a value. When you make a function doing something on a tree, it takes an argument that is a tree and produces a new tree. So second part is that within F# there is a very powerful type system, so a well-typed program will actually not go wrong. So it's not so that you will suddenly add a number to a string or get a null pointer exception, at least when you are using the pure functional part of the language. F# is combining object-oriented and functional features, and that is why there still are some null checks left in the F# code for this example here. Okay, so this is some features or characteristics of this project. What I would like to go into a little more is how do you actually construct a functional program, because you're surely not starting to write a class diagram or when you design a functional program, you're using some other methods. And the methods I will be illustrating today is try to see how do you arrive at a functional program, how do you design it. And my entrance to that will be a very concrete, simple example that can illustrate some of the features here. It's that of a family tree, and it's surely not deliberately an example you can go that can bring in some money, but I can use it to illustrate some major points. So here Larry is the ancestor, a male born in 45. He has 2 children, Paul and Mary, and so on. I think it's pretty clear what this is. I'll use this example to try to illustrate that one can have a succinct functional program where the concepts from this simple application can easily be traced down to the code. So I'll use it to give a flavor of what is a functional program, what kind of functional programming techniques are in play here, and how can we use types somehow to guide, to make precise what we would like to solve and guide the further development. So this is the agenda that I will follow here. So let me start with a very simple example. Here is what one can say a simple model of what I would like. I try to model the data. There is a type called family tree. There are types for sex, male, female, name is just a string, and then I have year of birth, that is an integer. So then I want to have some functions to manipulate these family trees, and the first one, make person, simply generates a family tree on the basis of the name, sex, and year of birth. So in the beginning you're generating a childless person. Then you can insert children in a family tree, and for a person with this name you can insert this child in a tree with a given ancestor, and what you get as result is a new tree. And then there is an option here, because it's not always a meaningful operation if you're trying to insert a child that actually is older than the ancestor. So there should be some intelligent checks there. Okay. Then you can try to find the name of a person in a family tree, and what I would like to have, if the person exists, is his year of birth and the names of all his children. So here you can see a type system used where you can actually build type expressions here. Here you have a type for a pair consisting of an integer, year of birth, and a list of names. So now my claim is that actually this is pretty much self-explaining. It's not needed to say a whole lot of more information to see what is the intent of these functions. So what I'll turn into now is to show how can we make this library, and by that illustrating the things that make functional programs compact, succinct. So I'll show you the use of a value-oriented approach, where I use functional decomposition and actually construct programs that will follow in a way the way I make the types here. Okay? So this is the agenda that I would like to hold. So at the end of the lecture, I hope I have presented a program and you can say, okay, I believe this is a correct program, or you can understand what is going on here, even though I guess very few is familiar with the language as such. Have an idea that what can actually, by reading this and spend a little effort, understand what is going on. So functional programs are easy to work with. Suppose now I have this already made library. Then I can make 3 persons here, 3 children, Stan, May and Jane. And if I want to make this family tree up there, I make a person for Mary. That is, I get the family tree for Mary. Still childless now. But here I repeatedly insert. So here you can see there's a function composition in green here, where I combine a fold back function that repeatedly applies another function to the elements of this list. So I will not go into detail about the definition of F# or this function, but just say that this is a repeated insertion. So I'm folding or repeating the function insert Mary into this list. And I can inspect the value directly by the way I constructed the library. So you can see the family tree where children are indented in a suitable manner. Okay? So far, I have not revealed the type of family tree, and this one is just a textual representation. But when we do the implementation, we should define what is a type, and then we should make the functions. Okay? So now I should make a value, a type for family trees. And the type family tree has a constructor person, and that is actually read as give me a name, a set, a sex, year of birth, and children. Give me these 4 parts, and by using person, I can construct a tree of type family tree. And to get something of type children, I construct a list of family trees. So you can see here there is a mutual recursion among the 2 types. Family tree depend on children, and children depend on family tree. That's the way it is. And actually, the way I will construct the program will reflect this structure. You can also see this is a way to build big tree, type for big trees, and the type declarations as such are very compact. Hopefully understandable also. Here again, what you see here is that I'm just building up family trees. I can write down a family tree for Stan, Jane, and then I can write down a value. This is a list containing 2 elements, Stan and Jane. And here I have a value. It's a list of family trees, and the system actually displays it. So it's very easy to experiment with functions. You make them, you try it out in the interactive environment as I did here, and you'll immediately see what is going on. So here is the way I can write down the family tree for this little family tree here. So this is Mary Prime, is an F# value now that you can use in the further examples or development. Okay? So basically here, what is important is on the top, succinct, mutual recursive type declarations for family tree, and that is the basis. So now I would like to hopefully show some understandable functions. How can I try to insert a child in a family tree? So there is something I should take care of. A person is elder than his children. Okay, otherwise it's not meaningful. So here is the function insert I should define. This child that is born this year should be inserted as a child of a person with this name in the family trees down here, characterized down here. So what is with green here are actually patterns for the ancestor in which the insertion should take place. So it's a pattern for a family tree. And in the case that the ancestor is born later than the child, okay, it's not meaningful. So in this case here, I don't give a family tree as result. I simply say none. There's no value here, or just the value 1. The second pattern here is the case where the name of the ancestor is the same as the name of the person who should, for whom I should insert a child. So in this case here, I build up a result. This is a tree, so the value has the kind sum family tree, and the person is the name of the ancestor, sex, year, and so on remains the same. However, the list of children now have an extra element, and this just reads, put this child in front of the list. So here you can see I'm constructing a tree as result, and in doing so I'm constructing a new list of children. Okay? So the last part here, I know that none of these two patterns fits, so I should try to insert the child in the list of children here, and this is done using another function I'll address later on, where I insert a child in a list of functions. I branch out on the kind of result. If this insertion is not possible, okay, the person is not in the tree or something is wrong with the age. So I return none. Otherwise, I get a revised list of a new list of children here, and this is the children list I use in my result. Okay. So some important cases here is that I hope this function is understandable on this slide alone. The cases are covered very clearly by patterns. I think even though you may not understand the details, you can simply discover this is a case, this is a case, this is a case. And some technical details is that family trees in this case are constructed in the sum expressions here. This function, try insert in list, actually you can see that the recursion here follows the structure of the type. A family tree is defined in terms of a list of children, so here I use a mutual recursive function, and so this structure of the function is not something magic, it's actually just following the data in a sense. And I'm not having null pointers here, I have none in case that, okay, insertion is not possible. So this was one part of the function. I should define this try insert in list in mutual recursion now. And now this is actually very simple in a way. So what is going on here is I look at the first child in a list, should find out should the insertion be done in this. Could the insertion be done in this child? If I get some a sum result here. I know it's the case, and this revised list is my result. Otherwise, the insertion could not be done in the first child, and I just progress with the remaining list of children here until I get things done. So this is actually a straightforward recursion following the structure of the list, where I'm done when I reach an empty list. So there's nothing very much interesting going on here. I just iterate through the list and insert when it's possible. So the structure here comes from the type declarations. So actually, when I consider the empty list and a non-empty list, there are no more cases. So I can look at this and say, okay, every kind of list is covered in a pattern. So this is a pattern for a list with a first element and a tail of the list, or the rest of the list here. If I look at every kind of result, there are these. When this function returns either the value, the result has form none or some child. There are no other cases, so this is also fully defined, and the same for here. So actually, every kind of result for the functions are covered in a pattern. Some of the things that makes this compact is that I can use such pattern, such constructors like sum, none, cons is it called, and for the list constructor in patterns, and I do that to take these composite values apart. So I have a list, I have an easy way to speak about the first element and the rest of the list. On the other side here, I use these constructors to build values. So the constructors have different roles in patterns and expressions. Okay? So the recursion follows the structure of the data type. So actually, by using these arguments, non-termination is not an issue. Each function will always compute a result. And if I forget one of the patterns, actually it's it's detected at compile time. So the compiler can actually check if I forget some pattern here, then it will say, okay, pattern matching is not exhaustive, and I need to consider whether I want it or not. So it's not something that I certainly get to know at runtime. I know it at compile time. Okay. So let's try to see. So I hope this was somehow understandable, even though you have not seen F# before. So this slide here, so say what should happen if I want to have a further constraint invariant, that I want that the children should appear in order of decreasing age. The youngest child first. Where should I change my program and how should I do it? Then it's very easy to look at the cases here to see, okay, this is the way where I actually insert a new child among a list of children. So this is the case that should be changed, because this may violate the red invariant I have up here. So the adaptation is actually very easy. There are several ways of doing it. I invent a new function. It's a function I can use to insert a child in this list before the first element in the list satisfying this predicate. Okay? I will return to this function in a moment, but believe me, this is what it does. And here is how it's declared. So it's a function taking a predicate, a function from some type to truth values, an element, a list, and gives me a new list. So, what is the idea behind this? Either I have an empty list, in this case, I have a list just comprising the element E as result. If it's a non-empty list, I need to distinguish whether the elements should be inserted before X or not. If P of X is true, it should, and I build up my result. E is the first element, X is the next element, and tail is just following. In all other cases, X should be the first element in my result, and I insert E before the first element, satisfying P in the tail. So this is actually a kind of standard recursion that you have seen before. Now I will not show you that many things about this was not that. Sorry. Yeah. Yeah. So here's insert before. What I would like to show you now is just, it's very easy to work with this interactive environment. So you make a function and you can try it out immediately. So here's the declaration. I copy it to the interactive environment. I want to insert before the predicate. It's a function of x given by x greater than 2. And the element I want to insert is 3, and it is in the list 2, 4, 5. And I create a new list where we can see 3 is inserted just before the first element that is greater than 2. So this is not a particular interesting example, but it shows you the kind of way you're actually working with this system. You can immediately get a feedback on the programs or the program designs you have, because you can just run it in the interactive environment. Okay. So, this was more or less the example I just showed you online. So the remaining examples I can simply just make. I can create now family trees for Mary, Fred, Paul. I can use my functions, and I can repeatedly do some insertion that I spoke about. So this interactive environment is actually very useful to give immediate feedback on what you are doing. The other thing that is very clear here is that you see that lists and trees are straightforward to create and use. There's simply no overhead in doing that. So let me give you some other ideas that now you have seen one function on family trees, but the ideas used there is actually reusable in other situations. Here I want to make a function try find, that for a given person with a name in a family tree should find his year of birth and the name of all his children somewhere in the tree, if is present. So again, we can find the mutual recursion following the structure of the type definitions. And in this case here, it's simple. If the name I look for is that of the ancestor, then what I return is the year of birth of the ancestor, and then I need to extract the names of all his children. And I'll not go into details. I use a library function on lists, which maps a function on all elements on the list. And in this case here, it simply just selects the names from the children occurring in the list. Now, if the ancestor is not the person I'm looking for, I have to look among all the children of the ancestor, and this is a recursive function doing that, and it's really doing it in the same manner as before, so I'll not cover this in detail. Again, in the interactive environment, I can simply just using it and inspect whether I got the right thing. So here is that, oops, so something went wrong. Yeah. The ideas behind these functions is that we are actually constructing a program by combining well understood functions. And in this case here, I'm combining try find with try find in list, and this well-defined function map from the library, where you can see what does it do. I map a function on a list, and I get a list of values obtained by applying f to each element. So this is a very well-defined and natural function. So I'm just using well-defined, understandable functions here, I hope. And in general, what the aim is that you can actually comprehend a function on a slide or page. You can comprehend what you are working at on a single piece of paper or whatever. So try to keep the analysis local, and of course not having global variables and something like that makes things a lot more local. So my major goal here was actually to give you some idea about what is a functional program. How are you going to go about when you construct a functional program? My assumption was that many of you before have heard about a functional program. Very few have actually written one, at least written one during your professional time. And if you did it while you were at school somewhere, then it was perhaps just in a single course where it was somehow used in isolation in that course. So my idea was that you have some idea how to make what is a functional program and how do you construct it. The approach here is actually very simple, naive you can tell, but I think it's surprisingly powerful. The idea is simply you have a topic, you name important concepts, nothing new in that, but then you specify types for the concepts. And what you have here in these languages is you have a very strong type system where you can have type operators. You can combine them in many ways, so you can really make composite types. Okay? When you have done the data modeling, here you specify type for the important operations. The construction shown here was actually very simple. Once the data model is done, then part of this program construction actually just follows the form of the types, the data model, you may say. So this is the basic part of the process. The goal of the constructed program in the end is that programs are constructed by composing small, understandable pieces. And this is, of course, very easy to say. In general, one can say that the functional languages in general support that. Libraries, the program techniques, the form of the language. But of course, the insights, it's not coming for free. Insights is always coming from the developer here. But the languages and platforms, I think, supports that you can actually construct well-understood programs by combining well-understood parts and get a succinct or hopefully correct program. Okay? So, That's the end of the talk. So you were very quiet. Are there any questions?
Do you happen to know, or maybe have statistics, how popular this F# is right now worldwide? Is big popularity growing?
Oh, it's growing rapidly. I think I see in the Copenhagen area where I come from, I see it's coming for in the financial sector for two reasons. One is that they would like their programs to be correct, and it's. I hope I have illustrated here some of the features here supports that you can express yourself closer to the problem area than in other languages, perhaps. So this is one part. The other part for that sector is that they have massive amount of data and are doing time-consuming analysis. And here you have seen no mutable state, and that means the programs are much easier to parallelize. So I see in that sector actually is using functional programming very much. Some are using F#, I know, others are using other functional programming techniques. I think it originated in financial sector in New York some years ago, where they used OCaml to do financial transactions, to make financial transactions. In general, I think that after F# became available on the .NET platform, suddenly functional programming was supported in an industrial development environment, and that attracted a lot of attention. So it's really being used much more now. And I mean, here you have the possibility to use F# for what F# is good, and if you would like to use some other components, database or graphical user interface or something like that, it is on the platform and easy to combine. So it's not some particular piece. Either you use that and nothing else. It's combinable on this platform with other tools and languages. So, yeah.
What about the speed of the Spanish and how the compiler works?
So, basically what it does here is that it compiles in the same manner as C# compiles, and it uses garbage collection, and the memory management system is the same. So in general, it is as efficient as the F# programs, equivalent F# programs. I did some measurements. There are some techniques for transforming recursive functions to a certain form called tail recursive functions, and those are the recursions that can be translated to loops in a simple manner, and there the tail recursive functions actually were faster than the corresponding loops because there were special instructions to deal with tail recursion. Okay, it was just a little faster, but it is as fast as the C# code in general. So there's no reason not to consider for F# for efficiency reason, because if the alternative is C#, it wouldn't be better. In general, there are good techniques to handle something like stack problems that you can actually avoid using the stack. And so, yeah. So there was a time out here. I think I could take a question, if okay. You're very polite, and that's so. Yeah.